So we were in the previous lecture going through the AFM lithography, and which is atomic force microscopy based lithography, and you can see that because when we have a nanoscale pin which can go anywhere and write on a nanoscale, so you can do many different things. So one application was doing the oxidation, local oxidation, by using the AFM. So the idea is, let me show you just first there was a nice animation, or this is not the, I think it's on the other page. Let me see. There is a one here. Okay. Okay, there is a problem with the flash. Okay, I think I don't know how long it will take, but let me see, just if we can do it quickly, then maybe. Otherwise, you can actually watch this link. Okay, it's quick. I think I am redoing it. Okay, let me just run one more time. Let's see. Okay, looks like it's still not working.
Just click the thing that says click.
Okay. Click to use flash. Oh, okay, use every time. Okay, fine. So this is a atomic force-based microscopy, vessel oxidation lithography. So you will see that there's a tip which is coming down, and now in the water, you can apply voltages locally, and you can oxidize the material. In this case, the orange layer. It can be silicon oxidation. It can be some other oxidation. Let me just run it one more time. It's just a silicon tip. You bring it in a water layer, and if this is silicon, you apply high voltage, and that high voltage actually allows the silicon and oxygen to react, and then you can locally oxidize the material, right? And you can write on the surface. So this is the one way we can use AFM for local oxidation. It can also be used to anodize different metals, like oxidized metals, for various applications. So, but again, you have a power where you can apply a high potential between a very sharp tip and a sample surface locally. So that's the power we get from there. AFM, again, in this case, you can, in this case, it just shows another image that you can use the tip and you can grow oxide in this case by applying a voltage. And in this case, you can also expose, you can expose the resist. Let's say this yellow line is the resist, yellow shaded area. And then once you apply voltage very specifically to a local area, then you can expose the resist to electrons in that very specific area. And that will break down, because when you apply voltage, there will be current flow, right? And that will locally heat up. And if you just keep enough gap between your surface and the tip, then the electrons will not flow. If you apply a very high voltage, then electron will jump to the other side, and that's kind of an electron gun you have now. And it's a similar way how electron gun is actually made. So in this way, you are making a nano electron gun, and then you can really focus on a small area. You can write it on a small area. A lot of people have used these techniques for various applications. You can also use photoresist. Let's say in this case, maybe as a AFM resist mask. And once you put it on the surface, people have reported resolution of sub 10 nanometer, and you can see the structure, which is very high aspect ratio, which was developed with the, and once you expose it, then you have to do development like you do in the photolithography. So, but the whole idea is to expose a certain area of a resist layer very specifically with the electron exposure. So that will break down the electron chain from there, and then you can develop it and make it a very small features on the surface. There is a very interesting article published in Science in 1993. So Science is a very well-known journal in overall, like Nature and Science. So these are very well-known journals. So in Science, people can publish stuff from all over different domains. So it's not specific to anything. So in this one, they have shown that they can arrange. For more details, you can go to the paper, but I just want to show you one example. This technique is called the scanning tunneling microscopy lithography. So where you actually apply very high voltage between the tip and the surface. So, and that potential, with that potential, you can push or pull certain atoms on the surface. So in this case, they have used a scanning tunneling microscopy to move atoms on another surface. So previously it was not arranged. So this one circular dot is actually one atom, and they moved it on another surface and they make a ring. There is also one very nice image which IBM has actually displayed everywhere. They have written IBM with the atoms on another surface by using a scanning tunneling microscopy. So, so you can see the power of these nanotechnology equipments, or the AFM-based lithography techniques, that how small you can control things. But again, you should not forget that for industry, we are normally looking for very high throughput methods, because that's very important. But in this case, it seems to be, it may find a lot of applications in a research and development where you want to see certain phenomena on atomic scale, but or it may have some applications. So maybe someone who is working in an industry in specific that area, he can comment more on that. But it may have also some industrial applications for certain things. Okay, there is another new topic. It's called the soft lithography. So it's clear from the name that it's a soft. There will be soft materials involved, and mostly it's the polymer materials which are involved in soft lithography. It's a very, very common technique, very common, very conventionally used technique nowadays in the laboratories. You still don't find a lot of commercial products based on soft lithography, like the real PDMS based soft lithography, but it is very, very commonly used in R&D nowadays, and there are new startup companies who are built based on this soft lithography technique. Then it really depends. So lithography doesn't gives you anything. it just gives you the power to make things small, but then why you're making it small, that is very important for the success of your business or product, like what you're doing exactly with that small thing. It may be in optics, or you're building a solar panel which are efficient, or maybe you're developing a biosensor which require a very small volume of blood to detect different diseases, right? So those applications still are being explored, and the people have some success by using solid lithography and developing microfluidic and nanofluidic devices. So briefly, in soft lithography, there is one technique. It's called the contact printing. In contact printing, again, there are quite a few variations. So which you are, some of them you might be familiar. One technique is called the relief, where you transfer an image from a raised surface coated with an ink. Let's say if you have a stamp, that's a perfect example. So if you have a stamp and you actually put in an ink and then put it on your paper, you will see the pattern is transferred, right? So we can do exactly the same thing on a micron scale or even a nanoscale. If your stamp has features in nanoscale, so then you can use that for printing, right? You can print many things on a surface. So that's the one technique, and that's called the contact printing. And you will see many, like in garment printing, people use a lot of these methods. And you can use some of these methods. You will see that later on to build the biotechnology-related devices. Intaglio is a totally reverse of that, where you have actually an inverse image, and then you fill that image with the ink, and the ink actually is sunken in those raised features, and then you put it on another surface, so then ink is transferred. So it's very similar to relief, but just the inverse of that. So lithography, you all are familiar with the lithography. We have been talking a lot about the photolithography, AFM, E-beam lithography, but lithography is a general process where you chemically pattern a surface based on their hydrophilicity and hydrophobicity. Screen printing is a very commonly used method to actually print the garments. That's what I know. And we are using in my lab screen printing method to print electrodes on the surface. So in a screen printing, there is actually a screen which you build with a method which has small pores on certain areas only. And what you do is you take a paste, let's say you take a silver paste or some color, and you put the screen on a garment or any other material, and you paste, in the paste you apply paste and then rub it, basically. So through those pores, the ink or the metallic paste actually go through the pores and start depositing on the bottom layer. And you can have very nice structure based on your mask which you have designed, and that we call it a screen in this case, because there is no photolithography involved. And you can still have a resolution in a few hundred microns. It's not very, you cannot print features very small, because making screens very small will be hard. So there are other methods which are more efficient, so that's why we don't use it for micro scale or nanoscale, but we use it for printing in general. There's another well-known technique used nowadays almost everywhere, electrophotography. So electrophotography is based on the principle that it's electrophotography, right? Looks very similar to photolithography, but there's electrons involved. So basically, people have discovered when you expose a certain metallic area with the light source, then you can ground certain areas. So you can dissipate charges in certain areas. I'll show you in a minute. And that's the method on which the xerography or our printing, nowadays printing, is based. I was reading about it, actually not now, but last year, like from where it came. And the xerography idea was actually, this technique was invented in 1930. And the guy who invented this method, it seems to be very laborious at that time, that how we can use it in daily life. But he said, okay, this is my idea and I want to sell it. Or maybe I work with a company, I can work with a company, or maybe you want to license it. So he talked with 10 different companies, big companies, and no one actually took his idea. And they said, okay, no, it's not useful. And then later on, there was one guy, interestingly, I think he says good luck, and he said, okay, why not, I will work with you on the company. And then they made a big company out of that, and you'll now see the printing and this technology used everywhere. So basically in this technology, what they do is, so you have a one photoconductor drum. So basically there is a circular drum. So where you can apply voltage and you can apply charge. So in this case you are applying actually a negative charge on all over the drum surface. Okay. So this is a negative charge, for example. So you're applying on a drum surface. Then let's say if we have a paper or image, then you shine a light that passes through the paper or image, and wherever there is transparent areas, then the light interacts with the, it's the same like photolithography. The light interacts with the surface, and then you will see that the negative electrons are grounded or diffused in that area, but they still stays in certain areas where there is no light exposure. And then there is a toner ink, which is also charged. So in this case, this will be positively charged. So when you, and ink has small particles in there. So, and those are actually, depends on what color you want to use it, but, and those particles stick with wherever there is a charge. Okay, so in this case, there is a negative charge, and the particles has to be positively charged. So they will stick with it, and then, so this is the first pattern which you generate actually on a drum surface. And then you slide a paper and you apply again a negative voltage, or you provide a paper negative charge, and then you slide it over a drum very quickly. And now this paper is more negatively charged, so that will attach the ink from the patterns, and the pattern will be just transferred in a reverse direction. Okay, so you can see that as paper is going on, then you are taking those ink particles with it. So in that way you can have actually that pattern what you have generated with the on the drum surface with the light exposure, slightly similar to photolithography, but we don't have a resist here. And that pattern is actually transferred to the paper surface like that. And now you can look at the speed, how fast we can do this process. Okay, so by looking at the process itself, it looks like maybe it will take some time to do it. But now, I told you earlier, when technology develops, you can make things much cheaper based on the requirement. Let's say if a lot of people want their product, then it significantly reduces the price. So yeah, now the printer you can get the one maybe reasonable $150 or something, which will work. Actually, even the color printers you can get the same price. Yeah, that would not be a fancy one, but yes, it can do the job. When we talk about the soft lithography, which is slightly different than the contact printing, there are quite a few different techniques which are further different types of soft lithography, but you will understand that you don't really have to memorize. You need to just get an idea, okay, what's in there. So for example, some techniques are based on micro contact printing that comes from actually contact printing, so like stamping. And that contact printing, so this is all techniques are called contact printing, and then once you do it in a micron scale, people put that under soft lithography. So yeah, that differentiation is not very clear, by the way. So, but there is a technique, it's called micro contact printing or nano transfer printing. So where you can print features on nano and micron scale by similar to the stamp method. In that case, your stamp need to be on that same scale or smaller than what you want to print. And in order to print a stamp, then first, yeah, you have to use a regular lithography or the E-beam lithography or ion beam lithography to make your stamp in silicon dioxide or some other material, and then you can use that for printing. There's another technique, it's called the micromolding. So let me just go through a couple of slides. I think then you will have a better idea what micromolding is. Okay, and there it has quite a few different types also. So when you talk about the soft lithography, if you know about this technique, you might also know about PDMS and polydimethylsiloxane, a very commonly used polymer and for a lot of applications. So there are quite a few good things about PDMS. And those are, let me just write it so that you can memorize it, maybe at least know it. So the first is PDMS. Advantages of PDMS. Okay. The first one is that it's a transparent, okay, the one thing is, you might also have seen it, that I'll show you again in the slide, that it was a transparent polymer actually. You can see things in from blue to red, anywhere, yellow, green. So all those wavelengths from 250 to, I would say, 800 nanometer, which is optical spectrum, and it's transparent to most of those wavelengths, which is good. So it means if there is something going on inside the channels which you will make in a PDMS, so that would be visible. And it has a good mechanical strength. I think it's a Young modulus is 1.2 megapascal. So basically, what does that mean? That it's not very rigid, and it's also not very soft, that it cannot retain shape. So it's a very it's a, I think, good enough rigidity so that it can maintain shape and it can transform into different structures. So that's one very good thing about the PDMS. And it is also actually porous for a lot of gases, but not for liquid. So, which is advantage? So it means it has some pores there. So if you have a gas, let's say if I'm growing cells, any kind of human cells, under channel, which I have made by using photolithography or by using soft lithography, and I want to incubate it in a certain environment where it need to have some gas exposure, because all human things require oxygen. So in that case, PDMS can be used because it will allow gases to exchange, but not the liquid. So whatever liquid will be there, it will stay there. So if you want to make a microfluidic and nanofluidic channels, for example, so this is one of the good material because it will not allow liquids to pass through it, right? So this is very, very good. So it can actually also withstand very high temperatures. It's chemically you will see some basically silicon based with a carbon methyl group backbone. So basically it's a polymer, and the good thing is it's chemically inert, so it's not reactive with most of the chemicals. So you can use it with the PBS, phosphor, buffer, saline. You can use it with most of the buffers which we use. Even it survives in the mostly acidic environments which we use for experiments. It also, you can clean it it is good with the ethanol and methanol also, but ethanol and methanol reacts with the polymer if you expose it for a long period of time. But in general, it's considered chemically inert, which is a good thing. It means if you're doing some reaction inside a small chamber which you have made in a PDMS, so this will not react with the chemicals itself. So which is very, very important.
Sir, what is after weight?
Sorry, chemical inert. Which one? Oh, withstand. Sorry for that. It can withstand high temperature. So I have used PDMS up to 500 degrees centigrade during the curing process, and it was fine. So right now I don't have the number exactly what is its burning or flash point or melting temperature, but I know it can survive a couple of hundred centigrade, so which is very good. Normally this is the range which we use to making sensors and detecting different things. Its composition is very homogeneous, which is another advantage. Why? Because so it doesn't matter if you make a big PDMS, so everywhere it will be having a similar composition. So it means if it is transparent one place, the other place it will also be transparent. And another important thing which I learned. Okay, by looking at the structure itself, it is a silicon and a methyl group on the surface. Do you think it looks like a hydrophobic or hydrophilic? Hydrophilic is the one which likes water. It means it need to have some charge and then it will like water, right? Hydrophobic is more oily, more no charge. So by looking at the structure, what do you think? Does it look like a hydrophobic or hydrophilic? Hydrophobic. So the PDMS is hydrophobic. There is no charge actually. Silicon has 4 bonds everywhere, and it doesn't have any charge. So that's why it's also chemically inert, and that's why it's also hydrophobic, right? But that's a good and bad. Good in the sense that it can contain, it will not react with the chemicals. But another thing, people who are working in this field, they might know better that when we are making microfluidic devices, sometimes we do need to functionalize those surfaces with some other chemicals or antibodies or proteins. So when we want to functionalize those surfaces, then functionalization of a PDMS is hard because it is inert. So from that perspective, it has some limitations also. But you can see that you can have a very clear, nice pattern transfer. So basically what it is there is that you have a PDMS at the bottom. You have your master, we call it a master, the one wafer which is sitting at the bottom. It has some pattern on the surface. And now you actually mix 2 polymers. So the PDMS comes in a base and the curing agent. So you mix it with some ratio 10:1 basically, normally. So you mix them in that ratio, mix them very well. You will see a lot of bubbles inside the mixture. Then you degas it. You put it in some degassing chamber, a vacuum chamber, so they will suck all the gas maybe after 20-30 minutes. And now the PDMS is ready, and you mix the bases, but it doesn't polymerize itself at room temperature. So basically, then you put your wafer where you have a pattern, and then pour it very carefully on the surface, and then if you let it sit for 2 days, it will solidify even at room temperature. But if you want to increase the polymerization rate, then we can use 100 degrees centigrade. At 100 degrees centigrade, it polymerizes in a few minutes, in maybe 5-7 minutes. You can also polymerize at 40 degrees centigrade, for example. Then it will take maybe a couple of hours to polymerize. So, but again, once it polymerizes, you can carefully remove the PDMS. Now it will be in a solid form. And now you can see in this image also that there are some patterns transferred on the surface. And I have used this technique, and it's actually very, very useful. You can have patterns even on nanoscale transferred with this polymer. I have been working at a micron scale most of the time. with these kind of PDMS based devices, but yes, it's very useful. Okay, and now you can actually you can make channels, you can make different structures inside this, and it's not expensive also. And I'll show you some examples, hopefully, in today's lecture. I have uploaded 2 papers, research articles, and there will be also homework coming up related to one of the first article. It's called the soft lithography, and there's a review article actually. And it talks about many things which we are discussing in a class and many other things which we are not discussing in a class because it's a very broad topic. So, and it's a long article. Okay, so it would be a good read, I would say. If you sit and relax, take a cup of coffee and start reading it. Okay, so it's like that. But some places you will not understand what it is. But then just go through it. When I was reading articles, so how I do it, when I am reading some article, and if I don't understand anything, which is very common, because no one knows everything, so then you start searching that thing. If you took a specific word, let's say protein crystallization, for example, if that word shows up in your in the article, so then you can start reading, okay, what is protein crystallization, for example, and then you read about it, understand it, and then come back to the main article. It takes a lot of effort to do it, and it requires a lot of motivation also. But yes, if you are really interested to learn about things, so this is the way to go. Learning is easy when you enjoy it, right? So it becomes difficult when you are not interested in a topic or when you don't understand things. So how we can make it easy? Then when you are reading it, then you understand things, then it's very, very easy. And how we can make sure that we are understanding the whole topic, then we have to actually sometime take some keywords and search what that is. And that is very important when at the start when you're reading articles and research papers, but when you are in the field or maybe you learn the field to some extent, then it's easy. I remember when I was working as a PhD student, one time my advisor asked me, okay, what is your progress actually in last week? And I told him, okay, I read this article, okay, in a whole week. And I also pointed him, I bring the paper, I highlighted certain areas, okay, read this, I understand this, but this I don't understand. He said, okay. He said, every day I read 4 to 5 articles. So this is a very slow progress from your side if you're reading one article in a week. But now I can read actually more than 5 articles if I want to read, maybe sometime very quickly, because not everything is important in an article, and that you learn it with the time, that what you are looking for and what you want to focus on, and that you learn it during when you do research work. That, okay, what is important? So there in a Google or Scholar Google, if you search one word, how many papers you got? Thousands of them in some topics. And then how do you choose that which paper I want to read, which may be more related to what I'm looking for different, you might have something in your mind, right? So that shortlisting, you learn it with the time. When you go through all this hard practice, okay, it starts harder, but then you learn, okay, what are the tricks, okay? But I will not go into those details now. But if you're interested, I can explain you a little bit. Reading abstract and conclusion and looking at the figures can give you half of the information that what's in there, and then what figure you want to look at, and maybe what section of the paper you want to read about. That you also learn it when you write papers, when you publish stuff. Then you know, okay, how to write it and how other people might have written their articles. So that kind of gives you some understanding. If you're on both sides of a picture, publishing and reading, then it's easier. Okay, so these 2 articles are uploaded online on Canvas, so make sure you read it, both of them, by next week if possible. And there will be homework also about the first article. I will let you know in a minute. Okay, in a soft lithography, basically the idea is that you have a hard master. Let's say in this case, our master is made in silicon, and this black features which are shown here, those are actually features which we have printed, which we have designed by using optical lithography or some other technique. So now it's a hard mask, or we also sometimes call it a master. And then you pour PDMS, let's say in this case, so this is your, okay, I think this is a photography process which he's trying to show you, but this is your master. And then you put a PDMS, which is now in liquid form, a gel form, like a honey, actually at that time. And you pour it on a surface, and let it sit for some time at specific temperature conditions. And then once it solidifies, you can easily release it from the surface. Okay, and then now you can see the pattern is transferred from your master to your PDMS stamp, okay, or PDMS. Now let's say if I take exactly this stamp and put it on a glass slide, what will happen? If I can bond it with a glass slide, if it sticks with a glass slide, then what you will see? You will see channels actually inside. In those channels, we can make microreactors in those small channels, right? Instead of doing things on a larger scale, you can do things in nano scale, nano volumes. So then you don't have to use a lot of material. Sometimes it's very important. If you're working with the gold, for example, just giving you a very broad example, and if you, in order to look at any reaction, if it takes maybe 10 ml, so you can do the same job maybe in few nanoliters, I mean, maybe one drop, and you can still get the similar results. And detecting blood, for example, some pathogens from blood, like viruses, or if you're detecting specific kind of blood cells, instead of taking a whole volume of a blood, which we normally do nowadays for analysis, maybe we just need one drop, because it may also have all the information, not for every disease, but some diseases the expression is very low. We really have to look at the large volume. But sometimes if you're looking at, let's say, blood count, CBC, right, which is very commonly used assay in a regular checkup when you go for doctor's office. So they look at white blood cells count, red blood cell count, then how many white blood cells are lymphocytes, how many are monocytes, and all that. You might have experienced that during your doctor's visit, but yeah, they look at all those things, but they all are there actually in the one drop also. So why we need then whole maybe 2 ml of blood, right? So it means then the idea is, okay, if we need a very small blood, maybe we can do it also at home if the things are adaptable to maybe with your cell phone or some other small devices which you can just get it and then use it at home. So that's where the future will be at one time. People even have thought about, this is a little bit off topic, developing smart restrooms, where you sit when you sit in the restroom, and it will have a lot of sensors, because in a urine you also have a lot of blood cells which shows up in a urine, and also in some cancer cells also shows up in a urine. So it already have some sensors which can sense while you're busy, and then once you get off, then it will, if it sees some signs of some infection or something in a urine, then it will let person know, okay, there is something going on, maybe you need to check with the doctor. So people are talking about those technologies right now, because other things we can do it in the lab, many of different assays, right? So, but this is maybe in, I don't know how long, 10, 20, 30 years, you might see some smart houses. People are already talking about smart houses, which is not mostly related with biotechnology, but yeah, smart cars, right? And you see some of the more development in that area, automated smart cars which can talk with each other, which will not be involved in accidents because they are controlled, they're talking with the other cars and all that. So so in that way we can have smart diagnostics also at home. And I know one of the quite a few people are working on an area where they install cameras in a home, and then they look at people, especially in old homes, if quite a few people are living there, and they see from their movement of their daily work, how they are sitting on the table, if they're walking and relaxing like that, from those postures. And by using the intelligent algorithms, they're trying to figure out, okay, from their just movement or their daily activity, can we detect any useful information about their overall health, instead of just employing some people there who are sitting there watching them all the time and see maybe who's maybe sick or not sick. So maybe if we have these type of cameras which are smart and we don't really need to maybe go there all the time, and whenever there is some problem or whenever you see that okay there may be some issue with this person, and then you can actually go and visit that guy and see what's going on. Okay, so yeah, there are I have seen some work done by groups in that area, and I think it's going forward further. There are also smart beds. We were also working on a proposal where people who are really sick, who cannot move, sometime after surgery, or maybe if they have some neurological problems or some other issues, and then they sometimes urinate on the bed when they're sleeping, right? And so when they urinate, what happens? The nurse or the other health professional doesn't know actually that he has urinated, or maybe if it's the night time, we are all humans, and they also have other patients to take care of. And then what happens that because of the urination and in the bed actually, and if the person also has some other infection going on in that leg area, and it becomes wet, right? So it can actually spread a lot of infection if the person stays there for a longer period of time. So whenever the bed is wet, so it has to be cleaned and changed. So we are also working on a project. We are thinking for VA people to VA hospital, one hospital, and writing proposal about that, and see if we can develop a smart bed sheets or disposable bed sheets which can detect, and which is easy, very straightforward how to do it. I think, in my understanding, it has a lot of other components attached to the project, a lot of other components attached to it, but one of it was detecting if the bed is wet or not. And we can just apply electrodes there, right? So we can have some conductive material, a paint, which can be in a design form, and 2 lines on the bed, right? And but then it has to be attached with some impedance sensor, which can be portable also. And I think you, excuse me. You work in impedance sensing, right? Okay, so by the way, so yeah, you can develop a smart and small impedance sensors, and those sensors can, then whenever, let's say, if the impedance changes to some level because of a urine, then you will see some beeping or something, so it needs to be changed. So like those kind of things. So there are quite a few different applications, and people are going towards the smarter things. Like smartphone is the one, right? We already have a lot of innovation in this field, but now how we can involve smartphone with the health. That was more about the presentation, right? Which was there on Tuesday. In my lab also we are doing some stuff on a smartphone-based sensing, and also some other applications. But basically the idea is that in the cell phone it's actually whole computer, so why not we can use it? Everyone has the computer, the cell phone, so we can design some attachments which will attach with the cell phone. There are quite a few groups actually. One at UCLA, and yeah, I think in San Diego also. Their main focus is develop actually systems which are compatible with the cell phone and for various different applications. Right now, it's a little bit hard to see how people will be using cell phones for many different applications, because if the adapter which you have designed need a cell phone, then it need to be very quick test, because if it is a very complicated test which you are doing, then maybe we don't need to do it at home. So at home it should be very straightforward and simple tests which you can use it and maybe dispose of the thing. But if you build structures which are very complicated, involves a lot of optics, and you are showing that you can do maybe flow cytometry, for example, with the cell phone, that is good to show that, okay, cell phone can be used, but I don't know what would be the point to actually develop such a system, complicated system, where you are just replacing a microscope with a cell phone. Then if you're building a complex system, just put a microscope there also, right? So that kills the purpose if you start making things very complicated and attached to the cell phone. So I don't like that idea, but I might be wrong, by the way. So I think whatever you are making with the cell phone or attaching with the cell phone, it has to be less complicated, so with the focus that people can use it at home, okay? But coming back to where we were, so So for soft lithography, we can use this PDMS, and we can design these channels, which can be used for a lot of different applications. And this master, which we have designed, it's basically designed with a photolithography. We can also, let's say, if I want to have this kind of a pattern, I can also do DRI, right? Deep rectified etching, to etch certain areas, but again, it requires some masking layer which will not be etched away. So, but PDMS is more easier to do it. Let's say now, if you have a stamp, you pour PDMS, leave it for 5 minutes, 100 degrees, remove it. Pour another PDMS, leave it for 5 minutes, remove it, right? So in that way, you can have many devices and channels from one master only, right? And just need a polymer. So that's the beauty of this technique. So the PDMS is also used for transferring the SAM layer or a self-atomic monolayer, right? Or any other ink. For example, this PDMS, now whatever you have designed, you put it in some ink or some let's say phospholipid bilayer, and now if you put it on the surface, then wherever there is a raised area, it will touch this silicon surface, and if it shows the binding of silicon surface, in that way you can transfer pattern, okay, on a silicon surface, in that way, or any other surfaces. And this ink which you're transferring, it can be some DNA also. This is a negative charge. You can transfer in certain areas. Proteins also have charges. So many biological molecules have actually the charges on the surface, either positive or negative. So that you can utilize to do many different things. So one example. So in this case, they have used actually gold N-thiol bond. So basically this substrate was made up of a gold, and then the ink had some thiol bonds in there, and then they use it to transfer the pattern from stamp to on the surface. So you can read this paper for more information. So basically, but you can see that this is 100 micrometer, and this, so somewhere here in the middle, you will see some features are actually very, very small. There might be few micrometer. So by using this technique, you can actually transfer pattern from one place to other place. There is another similar method. People have used soft lithography in one way or other way. Some techniques have advantages or disadvantages, which you will see. But for certain applications, one technique might be beneficial as compared to the other one. So this is micro transfer molding. So in this case, what you do is you first actually make a PDMS mold, then you put another polymer, then you clean the polymer from the top, so the polymer only stay the areas where there was a recessed features, and then you actually transfer that on the substrate. So wherever there was a recessed feature, there you will see this yellow material which you want to put on the surface, so that will stick with the substrate, so not the one which is a raised feature, right? In this case, only the raised surfaces were transferring pattern onto the silicon, but in this case it's a little bit different. It's kind of reverse. So that's called micro transfer molding. So that's why I told you there are quite a few different ways people use this technology, and sometimes one technique works better for certain applications or not. So micro transfer molding, again, you put a pre-polymer, remove excessive pre-polymer, put the PDMS on the surface, cure it, and then remove the PDMS. This black lines will stay on the surface. Then there is a micro molding in capillaries. That's called a mimic. There's another technique where you first actually put a PDMS on the surface, attach it with the surface, and then fill up the polymer and put a drop on one side. So because of the capillary action, actually movement, this will go inside the channels because of the capillary forces, and fill up those channels, and then you cure it and remove it, right? That's, if you do it that way, it's called the mimic micro molding in capillaries, right? Another name, fancy name for the technique. And then there is another technique called the replica molding, REM. So replica molding, you have a PDMS in this case, and then on the PDMS you put another polymer. So now you are, previously we were using PDMS as as a pre-polymer, and we're putting on a solid substrate, but in this case you're using PDMS as a master, and you're transferring pattern to another polymer, and then you peel it off. So if you transfer polymer from one polymer to other polymer, then it's called the replica molding, but it's very similar to the other soft lithography techniques where you use a solid master to transfer the pattern. In the replica molding, you can understand that when you are pouring another polymer, whether it doesn't matter if it's a PDMS or a solid substrate master, like the silicon base, if you use this stamp for 500 times, for example, you will see that this stamp will start getting damaged also with the time, because whenever you remove the polymer from the surface, and if the features are high aspect ratio, then it will also produce some stress while peeling it off on the surface. So that can take off certain features. And this is one of the image. It shows you that if this is our starting polymer master, which shows features. Some features are the width of this. These are the AFM images, by the way. AFM images. The width of the line is about 60 nanometer. So it means some features are actually 60 nanometer wide. And then once you are transferring it, and after a certain time they have seen variations, let's say at the start it was 52 nanometer, then it becomes, with the usage, it becomes 49, then 47. Okay, very small differences you can get with the time. And you will also see that the features, if you look at this bar, then this one here start getting irregular from the top, so which tells you that maybe the surface is start getting damaged on the surface from the top. So those kind of things you will see very often, but still it's a very, very useful technology. Okay, now so far we have talked about all the good things about the PDMS and all other soft lithography techniques, but are there any issues which you might have figured out in a PDMS based lithography? Can you see some issues maybe? If you know anything about PDMS, or maybe if you, by analyzing the information which I gave you, do you think there might be some situations where maybe this type of technique may not be very good? I told you one thing, that it's very inert, right? That's one limitation for sure. It's very inert, which is positive, and in one way it's also negative, because you cannot really functionalize it with other organic or inorganic molecules, because then it's inert. So but there are ways to go around the problem. Based on my experience, it is hard still to functionalize PDMS as compared to other glass-based materials which are hydrophilic. Glass is silicon dioxide, so you can easily convert it into more hydrophilic surface. Each type of glass is hydrophilic, it's not hydrophobic. So if you take a glass line and put a water drop on there, it spreads, so it tells you that it's a hydrophilic. But if you will take PDMS, small chunk of PDMS, and you put a water droplet on top of it, it will not spread. It will become it will try to stay close to one another like a bead. So you will see that it's a hydrophobic. So yeah, but you can do certain processes to make it hydrophilic and then use it for some applications. But then the surface chemistry is tough, so you don't get a very good attachment of the power molecules on the surface. There is another issue with the PDMS, is that it shrinks while curing. So it's a 1% shrinkage, which is not a major issue. But whenever you put it on the surface, but it starts shrinking afterwards when you cure it, which is normal, because when you're curing it, all the chains, polymer chains come in a proper order, right, to solidify, and that shrink. So its volume, overall volume shrinks a little bit, and that can produce stress on the bottom layer. But that's not really important, I think. But the more important issue with the PDMS is the sag. Do you know what is sag? You might have seen the power lines and the sagging effect, right? So that sag is, because PDMS, normal PDMS which we use, that is soft. It's not very hard, and we also don't want it to be very hard, by the way, because it might become brittle later on. Because it's soft, that's why it's flexible. So, but if you have features which are thin and tall, then the PDMS, with the PDMS base, let's say if you have a PDMS stamp, which are featured with thin and tall, now you put another stamp, then they will easily bend. And then also, if you have features which are not very tall but wider, let's say maybe 100 micrometer wide and maybe 50 nanometer high, that kind of a channel, then it will sag because of its own weight, and the channel will not stay open all the time. So that effect is actually there we see a lot of issues, the PDMS sagging. And then some people have changed the polymer configuration by using vinyl groups instead of methyl groups. So they have shown that vinyl-based PDMS has more is 4 times more actually harder as compared to the regular PDMS, and they have shown that it can improve the some of the issues. So let's say in this case, I'm starting from the bottom. In this case, let's say you have very pointed features. This whole column shows SlyGuard 184 PDMS, which is a very normal PDMS which we use, and there is a H184. H stands for harder. Okay, so this is for harder, this is for softer. If you look at all different features, let's say the features which are thin and tall, in this case, you can also see that if there are features nearby, they can stick with each other because the PDMS is flexible, and you can see also the sagging effect. The top is a PDMS, bottom is substrate. When you put a PDMS on the top, then the sealing of that channel can touch the bottom of the chamber, the substrate, so that can block the channel. So they have seen that sometimes they don't see actually any pattern made in PDMS when because of sagging effect, but when they use the harder, they can see very nice pattern. In this case, they also have seen that with the regular PDMS, there is some attachment of some of the features with one another. The sticking, you will see the pattern is not transferred properly, but in the other case, it was transferred properly. If you look at the other features which is made the circular rings, they have noticed that it's more clear in the case of harder, but in this case, and the point I want to highlight is more important. When you have a substrate which is a black features here, black substrate, and if you put a PDMS on top of it, when it's softer, then you get a pattern something like that, which is not very sharp and pointed. But when they use a harder PDMS, they were actually getting a nicer pattern which they want in their PDMS. So, yes.
Is there some type of limitation to avoid getting results like that, or do you just have to use better?
No, yeah, there are some ways you can get around the problem. So yeah, but yeah, for example, if you highlight any of those, for example, if this is the case, if the PDMS is sagging, let's say, and you're not getting any pattern transfer, so most probably what you have to do is, it really depends what kind of channel you want to make. As I gave you example, 100 micrometer wide, few nanometer high, then you will see sag for sure. And then you may have to switch to the harder PDMS. But in general, if your channels are 10 micrometer wide and maybe 5 or 100 nanometer high, and you see sagging, so what you can do is, while doing the pattern transfer, you can pour less PDMS, so the thickness of the PDMS which you are putting on the surface would be lesser at the end after it cures it. After you cure it, so it's not sagging a lot because of weight issues. So there are some ways you can improve this to some extent, but it really depends where we are seeing the problem. But yeah, there are ways around it. Sometimes it sticks very badly with the bottom layer. It's hydrophobic, and if your surface where you are printing it, let's say your master is also made up of silicon, for example. Silicon is hydrophilic or hydrophobic? Okay, silicon dioxide is hydrophobic, silicon is hydrophilic. Silicon is a semiconductor. It has a silicon, all 4 atoms are shared with all 4 atoms, so it's a very stable material, and so it doesn't have any electrons actually to share. So so silicon by default is a very hydrophobic material. And let me see if we can show you some I don't know whether I'll get some images or not, but yeah, I didn't get an image. This might be, but if, for example, I think this is silicon most probably. So this is silicon. If you put a water on the top surface, it stays in a rounded shape. But if it's silicon dioxide, then it spreads like that on the surface. Okay. So getting back to where we were. So if you have a silicon and you put a PDMS on the surface, then it sticks very badly with the silicon. And the reason is both are hydrophobic materials, so it's not easy to peel it off. And because while peeling off your features are very small, then again you don't want to apply very excessive force. Then we can use a curing agent, the release agent, so some chemical. There are some options available which you can spray on the surface, and then you can peel it off in a good way. Okay? Yes?
Can the tendency to sag be exploited to essentially form valves or like peristaltic pumping?
Yeah, but once it sags, then it sticks with the floor. So,
so you can't just.
So you cannot really push it really badly. Yeah, that's a problem with the pumping. I don't think it will improve it. Okay, but I didn't also tried it, by the way. But I think some sag can be recovered and some would not be, I would say. Slideshow start from the current slide. And there are also some other interesting techniques which people have developed around microfluidics and soft lithography. And as one example, this is very latest work, by the way, published maybe in last 10-15 years, and cell phone based compact disc-based fluidics. It's also current area of research for many people. So it's a very good technique, by the way. I like it. And the idea is that you can design patterns on, like fluidic patterns, by using lithography, connect transfer, right? So we have quite a few options. It depends what we really want to do. So we can design patterns on the surface of a circular disc. It doesn't need to be the CD which we use. It can be some other material, but in the form of a CD. And then you can make different reservoirs, and then which are connected with the channels. And by using centrifugation, because what happens in the CD, how the head reads different spots on the CD, actually your CD moves, right? I don't know whether you're familiar with that or not, but and it's also it moves in different, and that's why you always see the sound that okay, something is revolving inside. So it moves and go to different places, and from where it gets the information and combine it to make to give you the information. So in that way we can control actually the speed of a CD, like a centrifugation. So if you attach it with a motor and spin it at a certain RPM, you will see that it will provide enough centrifugal force. If you put something, okay, if you spin it, will things move outside or inside? Outside. Okay, that's good. So they will move outside because of a centrifugal force. But let's say if we have, let's say if I have one reservoir here, let's say this one, and if I spin it at a very less speed, and they are connected with the channels right here. So if I spin it at some specific speed, not everything will move outside, because then it also depends on the channel width. The channels which are there and how they are connected, they will also provide resistance to the movement of a flow because of the channel width itself, and because of the interaction between the channel walls and the liquid itself. So at certain places you will see that only certain wells the liquid from certain wells will move to the other places, and other at higher flow rate, maybe at higher centrifugation, then most of the things will go towards the other side. So in that way you can develop a logic where you can move fluids, maybe some fluids at one time at some velocity and then RPM, and then other fluids maybe at higher RPM, like that. Okay, so that's the whole basic idea. And they have shown that they can use it And the idea is that you don't need to use any pump to move liquids inside microfluidic channels. You can just use a centrifugation force to do all those things. And on a CD, you can just, it may be already loaded with a lot of other reagents, so you can put a drop of blood and start spinning it. It may be already programmed, maybe 500 RPM for 30 seconds, 200 RPM or for this much time, and maybe 10 RPM for this much time, and leave it for this much time, and then maybe after 10 minutes, you can get the CD out, and there might be some color generation or some other sensing mechanism there on the surface. This is one example where they have shown, see, this is the beginning, and then this is a calibration, and after 622 RPM for some time, the liquid is transferring from this chamber to this, from this chamber to it's going to all the way to the bottom chamber, and this is the reservoir, and then now, once this one is transferred, then the first one is not getting transferred, I think most probably because of the capillary force which the channel is providing. And then you will see that this well is empty fully, but there is there's still a liquid there. And then this is a higher RPM, 1026. Right, so this was 622. So higher RPM. Now this liquid start getting drained to the waste chamber. Right. So you can find many different actually papers, but they are very recent. Not a lot of papers, but still there are a few groups who are working this technique. And then they have shown that they can use it for disease diagnostics and other assays. So you can use this method for that purpose. And I see. You can do mixing of different fluids together. You can do many different things. But the basic methodology is that these are some of the examples where how we can use. We still have some time. So where we can use lithography. Some area of active research is the protein crystallization. Cell culturing, PCR is a polymer chain reaction, which we'll go into detail later on. After the midterm, what those assays are, and we can also synthesize particles with this technique. And these are some of the examples where people have used these soft lithographical techniques to build devices. And for example, this one, you can see how complicated this structure is, and you can move liquids from one place to the place, and you can do many different things. Okay, we'll not go into detail what they did. But I just want to show you that there are many different things. In this case, they were mixing, so this is called the rapid mixing. So where you are making small droplets, it's called the droplet. Another technique is called the droplet microfluidics, where you can mix two particles or generate droplets of any solution. And let's say there's a green and red, and there is a middle channel. So the middle channel actually breaks them out. This side channel actually breaks them out, and how much flow you are generating here, that will decide the size of those particles and all that. So that whole technique is called the droplet-based microfluidics. And now each droplet, where you are mixing these two fluids, if you want to look at the reaction, how they react with each other, if they generate any color or not. So instead of looking at them in a tube, you can look at them maybe in droplets. And now you can generate maybe 1,000 droplets in a few minutes, and then you will have 1,000 samples to see how these two chemical reacts. Okay, and you can also generate particles with that. So yeah, there are quite a few applications of the droplet microfluidics also. Then again, droplet microfluidics in here, people looking at, in this example, we're looking at the protein crystallization. So this is a precipitant which allows the protein to crystallize. There's a buffer, a protein is coming from one side, so then you use oil. So these are kind of system normally work with the oil and water-based separation. So in this case, the droplets are actually water phase, and the other media which is transparent here is actually oil phase. So in that way you can generate actually droplets, and you can generate you can even generate microparticles with this technique, and you can see the particles are very uniform. So with specific flow rate, you will always see those microparticles, and which can be used for drug delivery, for other applications. This is one technique how you can use the microfluidics to generate particles. Before I discuss this, I think I'll leave that for the next class because the time is getting up, but a few seconds. So the homework 2 is due based on the paper which I uploaded. You have to just write 1 page about advantages and limitations of soft lithography. Due next week, just 1 page. Okay, so what are the advantages, and that from where you can get the information? From the paper which I uploaded. I think it's the time. Okay, but I'll also upload it.